Hi folks, my name is Greg Holland. I'm a professor at Caltech, and it is my duty and pleasure to introduce Deanne Coppejans, a postdoctoral associate in Sierra, which is the Center for Interdisciplinary Exploration and Research in Astrophysics at Northwestern University. Deanne uses multi-wavelength observations to study accretion and outflows in compact objects and explosive transients over a wide range of energies from cataclysmic variables up to core collapse. With that, I'll hand over to Deanne.
Good afternoon, everyone. So yes, I will be talking about white dwarfs today, particularly focusing on accretion and jet physics. So white dwarfs produce a wide variety of electromagnetic radiation across the full EM spectrum on a range of different timescales. In terms of variables, you can get them in binary systems with other white dwarfs, main sequence stars, or red giants, and you get variability due to the accretion process. You can also get buildup of this accreted material on the surface of the white dwarf that triggers thermonuclear runaways and produces novae, or even stellar explosions, so supernovae 1A, and white dwarf tidal disruption events. And in future years, when LISA comes on, we will be detecting some of the very closest white dwarf binaries in gravitational waves. So today I'm going to focus on one question. Do we get jets from all accreting white dwarfs? Specifically, I'm going to focus on this question to advocate for the case for strictly simultaneous multi-wavelength observations and very rapid response times in the future. So I'm going to take a step back and give you some terminology first. So in the top left of the screen, you'll see an illustration of a cataclysmic variable star. This is a white dwarf with a low mass main sequence star companion in an orbital period of a few hours, and mass transfer occurs via Roche lobe overflow. So a subset of cataclysmic variables have a mass transfer rate in a specific range that triggers an instability in the accretion disk. So mass builds up in the accretion disk over time, which switches the disk between a bright hot state and a cool quiescent state. So if you look at the long-term optical light curves of these objects, down here you'll see an example. Most of its time it'll spend in quiescence in a cool state, and then the system will suddenly brighten by a few magnitudes for a few days and drop down into quiescence. This is what we call a dwarf nova outburst. So all you're seeing here is the switching of the disk between a bright hot state and a cool state. So getting back to the main storyline, jets have been found in all manner of accreting compact objects and indeed in most classes of accreting white dwarfs. But until very recently, it was believed that cataclysmic variables were the exception to this rule, that they were the one class of objects that did not launch jets. And one of the main reasons for this belief is because we were not detecting them at radio wavelengths. We were not seeing evidence of a jet. And that had some very significant implications because CVs have indeed been used to constrain jet launching models in compact accretors since that time. These are very nearby systems with comparatively smaller magnetic field strengths. So they're very strong constraints on jet formation models. But since 2008, we've had a number of discoveries that have called that into question, particularly in the radio regime. So in 2008, SS Cygni, which is a cataclysmic variable, was detected repeatedly in radio. It was very radio bright. Moving forward a few years, the Very Large Array got a significant sensitivity upgrade. And over the next few years, through surveys of a range of different cataclysmic variables, we were able to show that CVs do produce significant radio emission. It was purely a problem with the sensitivity beforehand that we weren't detecting these objects. So for the CV people out there, we've detected nova-likes, dwarf novae, and magnetic CVs in the radio. And now we have the combination of meerkat, the radio precursor to the square kilometer array, and meerlicht, its optical twin, operating, and we're now doing meerkat observations of nova-likes and CVs as well. So how would we look for these jets if CVs are launching jets? Well, the main thing is to compare these to the higher mass cousins. So Greg's just told you all about jets and X-ray binaries. So this is just a basic illustration of an outburst of a system showing that we get different jet outflow stages across an accretion cycle. So here we have the X-ray luminosity of the X-ray binary versus the spectrum. And over the course of an outburst, we see that X-ray binaries move across this diagram in this Q-shaped manner. So all you really need to know here is that when it's moving across this diagram, you're seeing different components of the inner accretion flow. It's switching between the hard corona and the soft, optically thick accretion disk. So the optical depth of the inner accretion flow is what's moving you across this diagram. Now, in the hard state, we see steady jets. And as they move across to the soft state, we get radio flares associated with transient jets. So the question is, do we see similar cycles in the dwarf novae? Well, Kurting et al. 2008 asked this question. So here again is an illustration of a CV. And the key thing is that cataclysmic variables emit at different parts of the EM spectrum. So the disk emits in optical and the inner accretion flow in EUV or X-rays. This is different to the X-ray binaries. So on the right, you'll see light curves and EUV optical and X-rays. In the top, you'll see a optical outburst, and the red points give you EUV light curve, and at the bottom you'll see the X-ray light curve. So what happens is that as the outburst starts, material comes into the inner accretion flow region. So we get an associated rise in the X-rays. But at a certain accretion rate through this inner region, the optical depth increases very rapidly. So your X-rays drop off and your UV emission climbs. Moving forward in the outburst, we reach a point where the mass transfer rate through the inner disk decreases. So the UV emission decreases, beg your pardon. So UV emission decreases, and then the optical depth of the inner accretion flow drops, and you get a spike in the X-rays. So by comparing the X-ray to the EUV emission, you can get an indication of the optical depth of the inner accretion flow. So Kurting et al. Compared this to the X-ray binaries. So if you were to plot on the y-axis the optical luminosity, which gives you an idea of the accretion rate through the disk, and on the y-axis this indication of the optical depth of the inner accretion flow, you get a very similar diagram to the X-ray binaries. You get SS Cygni at least goes through this same Q-shaped motion. So if CVs are launching jets, and if they are like the X-ray binaries, then we would similarly expect to see radio flares associated with transient jets as the system becomes transitions to the soft state. And indeed, this is what they found when they took radio observations of SS Cygni at the correct time. So The important thing here is that this radio flare has been detected in subsequent separate outbursts of SS Cygni, and the emission is consistent with synchrotron emission, most likely from a transient jet. So despite having constrained jet launching models for years based on this, we now have some evidence indicating that CVs may launch jets. So another question is, thank you. So now the question is, do other dwarf novae show the same behavior? And the simple answer is we detect radio emission from other cataclysmic variables, and the emission is consistent with synchrotron emission, but it's not clear whether the emission arises from a jet or not. So here again, we have in gray a optical outburst of this main system SS Cygni, where the open points show you the radio light curve with these bright flares at the beginning. And the filled points show you radio observations of a bunch of other dwarf novae. Now, you'll see that in none of them did we detect the flare at the beginning. That's unfortunately due to the timescales between the points, which were on the order of a day or two. It's not possible to rule out that flare at this point. But the emission is consistent with synchrotron emission. So in the next few years, there are a couple of important questions that we need to answer. If you want more details, please see Coppejans and Knigge et al. 2020 for review. So the first question is the hysteresis in this Q-shaped diagram, is that comparable? Is it actually comparable between CVs and X-ray binaries? The next thing is we're starting to see radio detections of highly circularly polarized flaring emission in some CVs, some anomalous flaring in SS Cygni towards the end. So we need to investigate that some more with multi-wavelength observations in the future. Another thing is there are some alternative radio emission mechanisms that have been proposed, such as flaring from the secondary star or the accretion stream, or magnetic reconnections in the disk. So one of the key things that we need to do going forward is obtain high resolution radio imaging of cataclysmic variables and outbursts to get a model independent answer of whether CVs launch jets. So if I could ask Karen to please pull up the poll, I'm just going to ask all of you to make a quick vote on whether cataclysmic variables launch jets. Okay, great. So 67% of people think that cataclysmic variables launch jets, 4% no, and 29% don't know. Okay, so the key requirements moving forward to make progress on this question is one, very fast response time. So this emission is expected in the first roughly 24 hours of the outburst. So you need to get on source with multiple observatories only on a timescale of a few hours. The second is strictly simultaneous multi-wavelength observations are critical to figure out what's happening in the inner accretion flow and the outflow. The third is high resolution and very high sensitivity observations are necessary to resolve this emission, and CVs are very faint in the radio on the order of a few tens to a few hundreds of microjanskis. So we need high sensitivity observations to move forward. So some key facilities for this research, Meerkat, the precursor to the SKA with its combination optical twin Meerlicht, is going to make some advancements in this field due to that combined radio optical light curves. Looking forward, the NGVLA is going to make a huge difference in this field, given the high angular resolution of the observations and the very extreme sensitivity. The same goes for the SKA. So those are my main points. Thank you very much.
Excellent. Thank you, Deanne. I think we're almost out of time, so I'm going to ask one quick question from the Q&A. is there a difference in the light curve evolution between magnetized and low magnetized CVs?
Yes, so if you look in the radio, the radio emission from magnetized CV seems to be a short flaring emission with higher percentage of circular polarization. Whereas in the non-magnetic CVs, we do see variability down to timescales of a few hundred seconds, but we don't get as much flaring emission. We've only seen flaring emission in a few cases.
Okay, that's great. Thank you very much, Deanne. That's wonderful.